I'm Feryal Ozel. I am a professor of astrophysics at the University of Arizona. I like to study black holes and neutron stars, so I would say that's my specialty. I also look at galaxies early on in the universe, but more from the point of view of how they grew their black holes and how the black holes influenced them. So it's a bit of a black hole theme. A black hole is the most bizarre prediction of our theory of gravity. It basically is an object that swallows all light. In fact, it works like all other objects as far as our understanding of gravity goes, but it is so compact and so extreme that all light paths and all particle paths turn inwards. So it's a one-way street. Things can go in, but they can't come out. So in effect, it becomes kind of disconnected from the rest of the universe, and we debate whether information is lost in that process. We can see black holes through their influence on their surroundings. So far, we haven't had any direct picture or direct image of a black hole, but what we have is things orbiting black holes. So just like the planets orbit the sun, and even if the sun wasn't there for whatever reason, we couldn't see the sun, we would be able to infer its presence. We do the same for black holes. They have a pretty powerful influence on their surroundings. Gas swirls around them and heats up and emits light, and stars orbit around it, and if they are too close, they get swallowed. So through those influences, we can infer the presence of black holes and measure their properties. But so far, we haven't been able to see them. But there's an ongoing experiment. Some people call it crazy. I call it ambitious, of hooking up telescopes all across the Earth. And the reason is we want to take an actual picture of a black hole and see the light from the gas swirling around it, and where it comes to an end, the shadow or the silhouette that the black hole leaves in that surrounding light. And we're performing this experiment on a handful of black holes, kind of as we speak. When we have all the data from the telescopes, we combine it into an image, and in that image, we expect to see the silhouette or the shadow of the black hole. So what defines a black hole is its event horizon, that point of no return where light or matter is sucked in. And in the surrounding light, it leaves that black imprint, or we think it will leave that black imprint. So all our experiments in the Event Horizon Telescope are designed towards being able to detect that, the light, and where it comes to a sudden end. What we mean when we say we hook up telescopes, and we've been doing this for about 15 years now, steadily increasing the capabilities at different telescopes so they can be part of the Event Horizon Telescope experiment. What that means is, first of all, making them suitable for looking at the sky at 1.3 millimeters, which is the best wavelength to do this experiment in. So it means putting receivers on them that can see 1.3 millimeters, putting maser clocks on them, because when we observe a source with multiple telescopes from around the Earth, we have to time tag when light arrives with incredible precision, so that after the fact, when we combine the data from various telescopes, we can make them behave as if they were one telescope with the aperture the size of the Earth. And in order to do that, we need a billionth of a second precision. So each telescope has its atomic clock. And on top of that, we're recording so much data that we need specialized disks. So making sure that they have enough storage space, petabytes, to be able to record several nights of observations when we have the observing campaign. The Event Horizon Telescope isn't one telescope, it's a whole array of telescopes. And not only that, but some of these, what we call these individual stations, our arrays themselves. Our most powerful telescope on the array that we get time on as a collaboration is ALMA. It's in the Atacama Desert in Chile, and it itself is a huge, powerful array. So being able to bring that online as far as this experiment goes was really exhilarating. When we found the optimal wavelength to do this observation in, it's 1.3 millimeters, as we said. It's one of those wavelengths where moisture in the atmosphere could ruin the observation. So we look for really dry desert-like conditions, and we look for high altitude whenever we can. So the Chilean desert is one example, and there are many others. But our most special location, I would say, is the South Pole. So the South Pole telescope is taking part in these observations with its new receiver that was built at the University of Arizona. And yeah, it is very dry and definitely stable atmosphere above it. And it's a bit difficult as far as getting the data in and out. We literally have to ship disks, and we have to wait for the winter to be over to retrieve the disks and be able to combine those data with the other telescopes. But it's totally worth it. Our primary targets are two black holes. One is in our own galaxy. It's the big black hole in the center of the Milky Way called Sagittarius A star. That's the one that has the biggest size in the sky. It's not the closest black hole. We know of closer black holes, but they are much less massive. So it's the perfect combination of big and not too distant. So it's 26,000 light years away from us at the dead center of our galaxy. And our second target is M87. It's much farther away, but it's 1,000 times more massive than our black hole, Sag A star. So we lose a factor of 1,000 in distance, but gain a factor of 1,000 in mass. So it becomes comparable, a little smaller than Sagittarius A star. And we think the structure of the gas around that black hole is different too, because we can see two powerful jets coming out in multiple wavelengths, whereas Sagittarius A star doesn't have jets, to our knowledge. So it's also a good point of contrast. What is different about these two black holes? Will we be able to see something in our observations that point to a different environment? Is it the black hole itself? So those are our primary targets. And then we're looking at a bunch of other bright black hole sources in the sky, but not for precision tests, more for understanding how they behave. The reason why we use an Earth-sized telescope is because even when I say the black hole is big, it's of course completely relatively speaking. Its size in the sky is comparable to the size of a donut on the moon. So if we were trying to take like sitting here, trying to take a picture of a donut on the moon, that's the resolution you would need. And that's why we need these telescopes that span the face of the Earth, the surface of the Earth, and making them talk to one another. So there are technical challenges, just getting the telescopes ready. There are weather challenges because astronomers are known to pray for good weather before an observation. They typically pray for good weather on one site, like hopefully it won't be cloudy or whatever in one site where my telescope is. We were in a position where we were trying to determine whether we're actually going to use a night of observations, and we were in communication with 9 different locations. Like, how is your weather? How is your technical readiness? Are your disks ready? So just the fact that we got 5 good nights this past April in 2017 was a mini miracle, but we're hoping to repeat it next year in April. Black holes are unique in that they're a prediction of general relativity, but at their energy scales, we expect quantum mechanical effects to also kick in. And we know that we have a wonderful description of the universe in quantum mechanics, an equally wonderful description of our world, the gravity part in general relativity, but they don't talk to one another. They are incompatible at a pretty fundamental level. So one of the reasons why we like to study black holes is to see if general relativity breaks down at some point, or can we see any deviation at the scale of the event horizon of the black hole? Any clues as to where we should be going from here? This is very common in physics, because where our theories start to fail, either in comparison with other theories or in comparison with experiments, we get the clues for the next thing. That's what happened with Newton's law of gravity that led to Einstein's formulation of gravity. So that's what we really hope to see, actually, when we are dreaming. If we perform a test of general relativity and the size of the shadow turns out to be exactly what's predicted, of course we're going to feel ecstatic. But if it turns out not to be the same, so we can convince ourselves that we've looked through all effects and the shadow size genuinely deviates from expectations, we're also going to be ecstatic, because who knows, the next theory might lie there. One thing that I'm excited about, and probably others will be excited about, is it's a new technique. So right now we're applying it to black holes, but the concept that one can build an Earth-sized telescope, communicate with remote locations, and have the power to do these simultaneous observations is actually the future of astronomy. I think we're going to be able to use it for other sources other than black holes, and it will hopefully prove to be a powerful tool. So that's one thing I'm excited about. The other thing is, come on, we'll say we took a picture of a black hole. Doesn't get much better than that. So we'll see, for example, if Interstellar got it right, if our imaginings of black holes and our mathematical formulations of black holes are correct. So a picture is worth 1,000 words. So that's where we're headed.